Hello everyone, I am Professor Amit Nehete, currently working as an assistant professor at Department of Electrical and Electronics Engineering at MIT World Peace University, Pune, and research scholar at Bharati Vidyapeeth deemed to be University, Pune, India. My topic of presentation is non-contact power system fault diagnosis, a machine learning approach with electromagnetic current sensing. The title of my paper, accepted at Indonesian Journal of Electrical Engineering and Computer Sciences, is Non-Contact Power System Fault Diagnosis, a machine learning approach with electromagnetic current sensing, along with my co-authors, Dr. Deepak Bankar, Ritika Asati, and Dr. Chetan Khadse. The content of my presentation is in line with the flow of research paper, that is introduction, proposed methodology, methods, result and discussion, followed by conclusion and references. We know that traditional power systems have been rapidly evolving into more and more complex and interconnected network of smart grids. This demands the advanced monitoring and control through modern technologies. So the smart grid have been posing different challenges to achieve faster and more fault diagnosis, which is required to maintain grid stability and resilience. This necessitates intelligent technique-based diagnostic action, which includes the different techniques using artificial intelligence methodologies. Over the years, researchers have been effectively using different supervised and unsupervised machine learning techniques, such as neural networks, ensemble methods, to develop robust fault analysis framework due to their capacity to analyze large data sets and ability of extracting meaningful patterns and insight. However, inherent complexities of smart grid environment and complex transmission network demand more and more research in the field of power system. I would request viewer to refer to the papers mentioned in the references to have more insights into the literature survey. The recent literature highlights extensive research in ML algorithms in power system fault detection and classification. However, the data they have used to train these models is the current and voltage from the current transformer and voltage transformer, respectively. These authors have not considered the limitations of current sensors and voltage sensors during using it for machine learning algorithms. So there's an ample scope for further enhancement of protection schemes, exploring more potential into current sensing and voltage sensing. The problems associated with CT mentioned in the literatures are minimum 3 transformers are required, one for each phase, makes it uneconomical. Core saturation issue limits the CT performance, and due to physical contact, requirement of physical contact, we have to adhere to the strict safety rules. Also, in the context of smart grid, we are always seeking easy to install and contactless sensing system. So this research paper works on the limitations of current sensor and uniquely focuses on comparative analysis of machine learning algorithms applied to magnetic field data instead of traditional current and voltage in fault diagnosis of power systems. The figure 1 shows general power system protection scheme. We can see here conventionally current transformer is used to sense the fault current, and accordingly it is collected with the help of instrumentation cable. Then comes the fault detection and classification, location, and on knowledge of this, a trip signal is forwarded to circuit breaker. In proposed research, electrical substation, current transformers are replaced by magnetic field sensors, and relay will be replaced by a device which can use AI technique. So thereby, proposed research works at aims at intelligent contactless safe solution to eliminate these errors. This block diagram shows the proposed methodology for the comparative evaluation of machine learning algorithms researched in this paper. Typically, in a power system, current transformer senses the fault current and sends the trip signal to the circuit breaker. In our proposal, as shown in figure, instead of the current transformer, magnetic field sensors will be used. Thereby, it shows a source and load model connected to fault creating block. This fault creating block will create the fault and the current will be converted into magnetic field using the current to magnetic field conversion block. And the data of magnetic field is generated and pre-processed to give as an input to the machine learning algorithms, and it will be compared and analyzed at the later stage. So here, power system simulated here, the main block is magnetic field conversion block, which will convert current into magnetic field along x-axis and along y-axis. Different fault types will generate different magnetic field patterns, which will be effectively generalized and classified using the AI techniques. To design the intelligent system, it is important to apply the different machine learning algorithms to obtain the more and more accuracy. In this particular case, we have used several supervised and unsupervised machine learning classifier models, such as Gaussian Naïve Bayes, K nearest neighbor, logistic regression, random forest, support vector machines, and XGBoost classifier, decision tree algorithm, and multiple layer perceptron algorithms. These algorithms will be applied to the generated magnetic field dataset, and they will be evaluated separately for the purpose of detection as well as classification. Functional description of this algorithm will be available in the research paper. The picture shows the simulation of 154 kV transmission line used in this research work. This is a 28 kilometers transmission line simulated in MATLAB Simulink. A three-phase fault block will be used to create different fault conditions, such as triple line to ground, triple line, double line to ground, double line, single line to ground faults. Here, according to in the Indian context, transmission lines are named as R, Y, and B. These are the specifications of the transmission line used in this particular research. This is an actual transmission line between Simao and Demirki at the Turkey. The proposed system assumes a couple of magnetic field sensors in the vicinity of conductors at specific position, such that one of them will detect the magnetic field in horizontal direction and other will detect the magnetic field in vertical direction. The system resolves the magnetic field to obtain the local 2D pattern. In this slide, we can see the current flowing through the phase conductors in R, Y, and B. IR, IY, and IB respectively are mathematically expressed. This slide shows the mathematical equations behind the current to magnetic field block. The proposed setup consists of two magnetic field sensors at the right angles. There are two coils at the right angles, out of which one coil senses the horizontal component and other senses the vertical component of the generated magnetic field. The relation between current and corresponding magnetic field is given by H is equal to M into I, where H, the matrices of H, M, and I given by the equations on the screen. Here, D and Q are the positional coefficient associated with horizontal and vertical magnetic field. M is called as position matrix. And finally, the matrix of magnetic field is computed by the equation shown finally. Magnetic field analysis using this method will vary with location of sensor. In this particular study, the sensor has been assumed to be kept at right and left side of the conductors, though only one case is shown here, as result obtained in both circumstances will be same due to the symmetry. Moving ahead to the method. The first point in the machine learning approach is dataset generation and pre-processing. In simulated power system model, 12 different type of fault and non-fault condition with various specification have been created, and a table as shown in table 2, fault types are converted to fault types have been used to create different class label. Magnetic field values corresponding to the different faults have been collected, and binary fault indicators were added to dataset, 0 for 1, 0 for normal, and 1 for fault condition to generate the novel dataset. For fault detection, the dataset includes magnetic field component along with binary fault indicator. For fault classification, dataset includes 4 columns as shown in table 2, representing R, Y, B, and final column shows the class label as shown in the table 2. The slide shows the different performance evaluation criteria used in the research to evaluate the machine learning algorithms. Performance evaluation provide insights into the effectiveness and capabilities of various algorithms. Important matrices used are accuracy, error rate, precision, recall, F1 score, and ROC AUC. In addition to this, fit time and score time are also have been used in this particular case. Moving ahead to different steps used in the machine learning approach are can be seen on the slide. A systematic approach is followed here to magnetic field component dataset. The script is imported to script have been written to import essential libraries of machine learning such as scikit-learn, numpy, pandas, and a function have been defined to evaluate multiple models. Various machine learning models have been initialized, and 5-fold cross-validation have been performed, followed by training and testing on 80-20 data split basis. Additionally, it uses bootstrap sampling for stability analysis and organizes cross-validation results. Finally, test prediction and detailed classification reports have been prepared for each model to prepare the results. These are the different algorithms used for the purpose of fault detection and fault classification. Moving ahead to results. These results shows the instantaneous current waveforms and corresponding magnetic field patterns under various states of transmission line. Figure 6 shows the current waveform under normal condition, and figure 7 shows the corresponding magnetic field pattern obtained by plotting Hx and Hy, that is horizontal magnetic field component and vertical magnetic field component. We can note here that it is a circular shape. Further, Figure 8 shows the current waveform and corresponding magnetic field pattern under triple line to ground fault condition. Likewise, figures further shows the current waveforms under different fault conditions and corresponding magnetic field patterns obtained in MATLAB Simulink scope. Notably, here we can observe that each type of fault yields a distinct magnetic field pattern which lays the foundation of fault identification and classification. We can note that apart from normal fault, normal condition, in all other fault, magnetic field pattern from the circular shape have been altered. This lays the base of research that we can use these different magnetic field values to detect and classify the faults. Results now shows the results obtained when the dataset generated of magnetic field have been applied to different machine learning models. So this slide shows the comparison of accuracy and errors of various machine learning algorithms applied for fault detection. We can see here XGBoost algorithm achieved the highest accuracy of 99.98 and error of 224.44 microseconds. This slide shows the comparison of machine learning algorithms applied for fault detection. Here we can note that Gaussian Naïve Bayes, k-nearest neighbor, random forest, and XGBoost algorithms have achieved high mean scores across all evaluation matrices. However, Gaussian Naïve Bayes and k-nearest neighbor have exhibited excellent ROC-AUC score, along with weighted recall F1 score and precision values, indicating their effectiveness in fault detection. This slide shows the comparison of training and testing of machine learning algorithms applied for fault detection. So we can note here that Gaussian Naïve Bayes algorithm have emerged as the most computationally efficient algorithm, and random forest and support vector machine algorithm have exhibited longer fit times. This table presents the comparison of all the machine learning algorithms applied for the purpose of fault detection in this particular case. This slide shows the use of results obtained after the use of magnetic field data along with machine learning algorithms for the purpose of transmission line fault classification. Comparison of accuracy and error can be seen on the screen. It shows that multilayer perceptron algorithm have achieved highest accuracy with a low error rate of 2.68. So it is effective in fault classification for transmission lines. However, the algorithms have shown accuracy after that are k-nearest neighbor, which has accuracy lesser than the MLP, and then decision tree and random forest algorithms have shown the accuracy around 86%, but they have higher error rates, and Gaussian Naïve Bayes and support vector machine have achieved the accuracy of 81% and 81.79 and 74.72%. This slide shows the comparison of matrices of machine learning algorithms applied for fault classification. We can see here the k-nearest neighbor algorithm have achieved the highest overall performance with a mean test ROC-AUC of 0.8869. The machine the multi-layer perceptron algorithm have also performed well in this case. However, Gaussian Naïve Bayes and support vector machine have lower performance as compared to all other. This slide shows the comparison of decision tree and Gaussian Naïve Bayes algorithm. We can note here that decision tree and Gaussian naive Bayes algorithm have demonstrated the fastest training and prediction times, making them ideal for applications which requires high computational efficiency. Other than that, K nearest neighbor had shown low fit time but high prediction time, while multi-layer perceptron and support vector machine required more time for training purpose. Summarizing the discussion, we can note that for the purpose of detection, Gaussian Naïve Bayes, K nearest neighbor, random forest, and XGB excel, while for the classification, multi-layer perceptron and K nearest neighbor are superior. This table shows the comparison of various matrices for various machine learning algorithms applied for fault classification. Concluding the research, this research addresses the critical challenges in transmission line fault diagnosis in the context of smart grid especially. The study highlights the potential of magnetic field sensing, which can emerge as a non-contact, effective, compact, safe, and economical alternative to the current transformers for power system protection. We can apply machine learning techniques to magnetic field data to obtain the superior fault detection. Multi-layer perceptron and K nearest neighbor algorithms have excelled in fault classification. That underscores the potential of magnetic field sensor to, along with machine learning for advanced power system protection. So the takeaway of the research is magnetic field sensors integrated with machine learning represents a promising direction for modern power system protection technologies. These are the references. Viewers can refer to the research paper to go more in depth in this. Thank you. You can write us on these email IDs if you have any queries or if you have any collaborative proposals. Thank you.